Chapter 18, Section 2, we're going to discuss 4 main classes or types of nuclear change, which can kind of be separated into 2 categories, spontaneous and non-spontaneous. Of the spontaneous ones, we'll talk about radioactivity, and then artificial transmutations, which would be classified as fission or fusion, and then non-spontaneous nuclear change, which would be transmutation. For radioactivity, you're going to have a nucleus that decays and emits particles, either alpha or beta particles, in electromagnetic waves or gamma rays. Converting neutrons to protons is one way to stabilize nuclei. So if the NZ ratio that we mentioned in the last section is too big, the nuclei is going to decay. So these processes that we're going to talk about are ways to stabilize the nuclei. So if you're converting neutrons to protons, this is a form of beta decay, which is when you've got a nuclei that has too many neutrons for the atomic number, and it becomes more stable by decaying and then emitting that radiation. So the beta particle is going to be an electron that is a very high energy electron that's emitted from the nucleus when this process happens of changing the neutron to a proton. And this is the equation, the general equation that we would look at here for beta decay. And then this is a real example. So taking carbon-14 and converting that into nitrogen-14 with also one of these beta particles being released. Another way to stabilize nuclei is by converting protons to neutrons, and there's 2 ways that you can do that, one through electron capture and then the other through positron emission. Electron capture is when the nucleus has too few neutrons, so it will absorb an electron, which changes a proton into a neutron. They'll balance each other out. And the gamma rays then are the high energy, short wavelength, electromagnetic energy waves that are produced by decaying nuclei. So as the nuclei stabilizes, and it's going to release this gamma particle or gamma ray to help to stabilize. And this is your general equation for that. And then the example here of starting with atomic number of 24, emitting that, capturing that electron, and then being able to release that gamma ray and convert the proton into a neutron. So you would go down to the atomic number of 23. Another way to convert from protons to neutrons would be through positron emission, which is similar to beta decay, but a positron is emitted by the protons instead of the electron being emitted by a neutron. So the nuclei is going to emit positrons, which are called antiparticles of electrons. And here's our equation for that. And then our example here, again, starting with a nucleus that would have 24 protons and ending with a nucleus that has 23, and then that positron as well left over. Annihilation of matter is an event where a particle collides with its antiparticle, and then both are changed into energy. So positrons especially rarely make it to the surroundings before they collide with the antiparticle, their electron. So that can cause them to be annihilated from one another, and the result then would be 2 gamma rays that are going in opposite directions. Another way to stabilize a nuclei is by losing alpha particles. So with alpha decay, you're going to have a very large nuclei with too few neutrons that decays by giving off these alpha particles, which are helium-4s that are made from that decaying neutron. So here's our example. You're going to, they start here with uranium-238, and if it undergoes alpha decay, you're going to release this alpha particle, so your helium-4, which has 2 protons, and then the remaining part left over from that original uranium is going to be the atomic number of 90 and the atomic mass of 234. Okay, so these two added together would give you your original uranium, so you're splitting that apart and getting rid of that alpha particle. And then a decay series means that you're having several decay processes happen in a row. So a lot of heavy nuclei have to undergo decay several times before they actually get stable. No element above atomic number 83 are stable isotopes, and a lot will decay either through this alpha decay process or through electron capture. To balance nuclear equations, we need to make sure that the total mass numbers and the nuclear charges balance out on both sides of our equation. So in this example here, our masses have to be 234 because that's what we're starting with thorium here. So our masses on this side have to be 234, which it is, and then the charges have to balance out to 90. So we've got 90 from our protons here, and then we've got 91 from this, but we've got a -1 here, so we're able to balance that out. So it's very similar to balancing a regular chemical equation. We need to balance for both mass and charge. Nuclear fission is a reaction where you're going to have a large nucleus splitting into 2 approximately equal sizes, and that process will also then produce a whole lot of energy. A chain reaction is going to be a nuclear reaction that can sustain itself. And then critical mass is going to be the smallest mass of radioactive material needed to keep that chain reaction going. So if you were to get to that critical mass, that's the lowest mass number that you could actually have keeping that chain reaction going. For nuclear fusion, we're talking about 2 smaller nuclei combining to form 1 more stable nucleus and lots of energy. Reactants are going to be plasmas, which is a random mixture of positive nuclei and electrons. Solids just can't withstand the temperatures that you need to be at because you need very high temperatures and pressures in order to bring those nuclei together. This is how the sun's going to produce energy, how the hydrogen bombs are made. And then the last form here is transmutation, and that is when we create a new nuclei by bombarding a nucleus with alpha particles. So this is a non-spontaneous reaction. And through transmutation, we're going to produce an unstable compound that can stabilize by emitting a proton. So you can see in this equation here, this part that's in the brackets, that's the unstable compound that gets formed first, and then that will emit a proton. Here's our proton in order to form a more stable form. So this is kind of a modern version of what alchemists were trying to do when they were trying to turn, lead into gold. And very few alpha particles actually have enough kinetic energy to overcome nuclear repulsion, so it doesn't work with a whole lot of elements.